Have you ever wondered what a sinusoidal function looks like? If you're part of the normal population of people, probably not. But we can represent curves and graphs of trigonometric ratios. What this means is we can find what the graph of sine of x looks like for any x value. Further, we can look at cosine of x for any x value. How would we find out what it looked like though? Before we just jump into what the graph looks like, let's look at some of the behavior of sine and cosine for any given angle. Let's take a circle. After that, let's draw a random line and one that connects the right of the circle and label its resulting angle theta. Let's get a negative angle, which just reflects theta across the horizontal axis. We are met with 2 points. The top point is cosine of theta, comma sine of theta, since our x component is cosine and our y component is sine. If we looked at our negative angle, then our cosine, or x, stayed the same, but our sine, y, changed sign. We could generalize this for any random arbitrary angle theta by saying cosine of negative theta is just cosine of theta, while sine of negative theta is -1 times sine of theta. Now, what if cosine was a function of x? Well, we can further say that this function would be even or symmetrical about the y-axis. If sine was a function, the function would be odd or symmetrical about the origin. Let's look at something else really quick. Let's get some arbitrary line and connect it to a point. If I rotate this line around the entire circle, clockwise or counterclockwise, we'll end at the same point. So if the angle made is theta, then theta plus 2 pi would be the same output. This is called a coterminal point, since when you rotate this line around the entire circle once, twice, 3 times in a clockwise or counterclockwise direction, it lands on the same point. In a normal circle, the angle's output is equal for every 2 pi n, where n is some integer that could be positive, negative, or even 0. So, since our function repeats infinitely in both directions and is either even or odd, we can find the shape of one portion and apply it throughout the entire graph. So, let's get some values and sketch a curve. Using our values from our unit circle for sine, we can see a shape of a wave being made. If we connect this smoothly, we generate a sine curve. Similarly, we can do this for cosine. Since this repeats in both directions, we can extend our shape to look like this. F of x equals cosine of x, for example, looks like this oscillating or repeating wave every 2 pi, marked by the lines. Sine ends up reflecting cosine of x to the right pi over 2 units. Now, let's look at some certain transformations of a sinusoidal graph. If f of x is equal to sine of x, then we can look at certain horizontal stretches, vertical stretches, horizontal shifts, and vertical shifts. Firstly, if you look at the counter, you'll see that our horizontal dilations squish our function or stretch them out horizontally. This changes our angular frequency, or our period, which represents how often our curve repeats. Secondly, vertical dilations change our amplitude, or distance from the crests, which are these top points, or the bottom troughs, which are our bottom points, to the midline. Thirdly, our horizontal shifts move our curve to the left or the right. And fourthly, our vertical shifts move up and down. Now, we have our general function. F of x is equal to sine of x. But we can account for every possible variation by the bottom function, a times f of b times x minus h plus k. This function accounts for horizontal shifts, vertical shifts, stretches, or shrinks. If we replaced f of x with sine of x, our general equation would look like this. A would be our amplitude, or distance to the midline. B would be our period if 2 pi divided it, or how often our original curve repeats itself. H would be our horizontal shift, or phase shift, and k would be our vertical shift. Let's look at an example. Graphing f of x is equal to 8 sine of 2 times x plus 3 plus 7 applies several transformations to our original sine curve. Firstly, it applies a phase shift of 3 units to the left, 7 units up, vertically stretches our function by 8 units, and applies a horizontal shrink of 2 units, squishing it by a factor of 2. If we draw our midline and draw a line to a crest, then the length would be our amplitude. Our next video will incorporate tangent and cotangent into this mix. Before I end the video, this demonstration of a sine curve can be demonstrated like this. This animation was created by Heejin Park. I use Manum, an open source API, to create these videos. I thank you all for the gratuitous support, and the necessary links will be supplied in the description.